Hello everyone. In this video we are going to talk about a third method for derivation of equations of motion for an n-link robot. So far we have seen the Lagrangian formulation and then the Newton-Euler formulation. We learned that the Lagrangian method has the advantage of working with energy terms and excluding the reaction terms, that the total work of them is zero, right? The Newton method has the advantage of actually calculating those forces. Sometimes we really need to calculate those reaction forces. That's where the Newton method can be advantages. And Newton method works with vectors. So in general, working with vectors is a little bit more time consuming than with energy, that is a scalar. There is a third method developed by Professor Thomas Kane from Stanford University in 1961 called the Kane Method, which has the advantage of not including the reaction forces for which the total work is zero. So it has the same advantage as the Lagrangian method, but it has some extra bonus advantages, like for example, it does not need to take the derivatives that you need to do in the Lagrangian method. And the bigger advantage to me is when you have constraints applied to the motion, this method can handle constraints a lot better than the Lagrangian method, because in Lagrangian method, in order to incorporate the constraint, you have to introduce some extra unknowns called the Lagrangian multipliers. In this method, we don't need to do that. So that's why in many commercial software packages for dynamic analysis of rigid bodies, robots, and so on, you see this method is used specifically, like in Adam's working model, the Pro or Mechanica motion, right, Autolev, and so on and so forth. So this method really is an interesting method, efficient method. And I decided to include that along with the two others. So what does this method do? So it starts with the D'Alembert's principle, that in D'Alembert's principle, basically, if I want to put it very simple, instead of the second law of Newton that you say F equals ma, if mass is constant, you say the second law of Newton is like this. The D'Alembert principle says, let's call this mass times acceleration a force, and we know it is called an inertial force, right? So it calls that F star, the inertial force. And then the D'Alembert's principle says, instead of saying F equal F star, you can also say the system is like in an equilibrium where the F and the F star are kind of canceling each other. So another way to describe it is to say F plus F star equals what? 0, where F is the actual force applied to the system by the external environment, and F star is the inertial force in the system due to the acceleration of components. So another way to write Newton equation is this. Good. Now, here we are dealing with vectors. In order to go from vectors to scalars, in the Lagrangian method, we multiply F by what? By dot dr, and we make it a work term. In here, it dot product both sides by the velocity. So it says V, if this is the whole thing is 0, then I can say V dots the whole thing is 0, the velocity of the particle. So right now, as of now, I'm talking about a single particle, but then we are going to generalize it to include the equation of motion for an entire system. So it says V dot F plus V dot F star is equal to 0. And you know from my lectures on dynamics, or probably your physics, that V dot F is what? Actually, that's the definition of power, P. Right? Power P is V dot F, or dW over dt, right? Because dW is F dot dr and over dt, correct? This dr over dt becomes V. So that's the definition of power, V dot F. So it says the power injected into the system through the external forces and torques is equal to the power that the system has due to its acceleration or due to the inertial acceleration terms or inertial forces. So this is like power in equals power out, or power in plus power out equals 0 if for one of them you consider positive and for the other one you consider negative. So it says the power that all of these forces are injecting into the system is used in the system to give it acceleration and velocity. Or just one of them really, acceleration, because velocity is an aftermath of acceleration. Kane, instead of defining V dot F as power, called this term activity. So it says A, which is V dot F, is activity of the external force F, and A star, which is V dot F star, is the activity of inertial forces, or they call it the inertial activity of the inertial force, F star actually here. Okay, so it says now activity plus inertial activity is equal to 0. Again, that's the same thing. It's just you're calling it some new term. Good. Now, what's the problem here? Well, the problem is this is very good. This is excellent idea if you want to describe the equation of motion for one particle, right? With 1 degree of freedom, that's absolutely fine, because if I have a single particle here, let's say moving on a surface, right, and I have this external force F, and I have the friction here, let's say Fk equals mu k times n, and you know I also have n and mg, and this block is only moving in the x direction with position x and or velocity v. If I say f dot v or v dot f plus v dot f star is equal to 0, v here is x dot times I. F here can be all of the forces, which is the capital F times I minus mu k n times I, then plus n times j, and then minus mg times j. And then plus, again, x dot I dot the f star, which in this case, in general, can be what? M times ax I plus ayj, the total acceleration of the block. This is equal to 0. And the thing is, when you do dot product, I dot I is 1, but I dot j is 0. So all you will get down here is going to be what? Is going to be f minus mu kn, the whole thing times x dot. And then here it is going to be, this inertial term has a negative, right? It's negative acceleration, negative m times a. So it's going to be negative x dot times m ax is equal to 0. And here, if you factor out x dot, is going to be f minus mu k minus max is equal to 0. X dot cannot be 0 because the system does move. So that means only f minus mu k n has to be equal to max. This is mu k times n. And that is, of course, the same as the equation of Newton. And you might say, well, why couldn't I directly say sum f equal ma, and the life would be a lot easier, right? Sum f in the x direction equal max, and that would be it. You're right. By the way, you know this n is equal to mg in this case. It is. For a single degree of freedom system, or maybe sometimes even two, but most of the time one, for 1 degree of freedom, the Newton method is extremely faster and easier than Lagrangian or Kane. The problem comes when you go to higher degrees of freedom. The Newton is not as easy to extend to higher degrees of freedom without including a ton of reaction forces, and especially when the constraint comes in. Lagrangian and Kane, on the other hand, are a lot better to handle more degrees of freedom, and Kane is even better when it comes to constraints. Right? So although one of them might be a lot better in the lower degree of freedom, but when they go up in the degrees of freedom and constraint, definitely Newton method falls behind. Okay? So that's amazing, right? If it can give us everything that it promised, and it will. The problem is this information included in this equation is not enough when the degree of freedom go beyond 1. Why? Because this equation is actually a scalar equation. You know, A is the same as power, as I said, and power is a scalar. So when you have 1 degree of freedom, it's absolutely fine. But when you go more than 1 degree of freedom, this V in general, this vector V and this vector F or F star, the way that they are written, they cannot give us enough the equations of motion. Like when the system has 4 degrees of freedom, this guy still will give us 1 degree of freedom, 1 equation, not 4. So Kane has to reformulate this to be able to apply to basically more than 1 degree of freedom. And what he did was, instead of dot product of V with F on both sides of this equation, he dot producted partial components of V, partial velocities, VR dot F, where R here is a variable that can change from 1 to n, and n is the degrees of freedom. So instead of multiplying, dot multiply the whole vector V by F, each time he only multiplied a portion of velocity of V by F, and that allowed him to acquire, because this R goes from 1 to n, this equation, when you expand it, it's going to give you n scalar equations, and you have n degrees of freedom, so now you are going to be fine. Okay, so definitely this new method can, that R should actually be there. This new formulation, as long as we know what VR is, can give us enough equations for enough degrees of freedom. So first, a terminology. This VR.F or VR.F star, which Kane showed by FR or F star R, they are called the rth generalized active force or the rth generalized inertial force for the particle or the system in the space, in the task space, really. So please pay attention to the fact that first of all, instead of the velocity, we are using a portion of the velocity, a partial velocity. And here, I also call these terms active force. I don't call them activity anymore. I call them active force. Why active force? So it seems like this FR and FR star are now of type force instead of type power that they used to be up there. Why? We'll see, because the definition of VR is actually not real velocity. It's just kind of like a direction of velocity. It doesn't have, this guy does not have the units of, let's say, meters per second. It has the unit of like 1. So FR and FR star has the same unit as F, and they are really forces. That's why we call them generalized force or generalized inertia force. And we also call them the Rth generalized active force, because they are really for the Rth partial velocity. Okay, we have R of these FR or FR stars. Good. So now, how do we define this VRs, right? Because that seems to be the major thing. So let's go ahead and talk about the VRs. So these partial velocities, or VRs, are coefficients of the generalized speeds in the terms of angular and translational velocities. What does that even mean? So in order to clarify that, I need to go through the steps of the Kane method for you. In general, this method has 8 steps that you need to take for any system with any degrees of freedom, and I'm going to go through that. And for that, I'm going to use the 2 degree of freedom planar arm with revolute joints, right? Because as we said, this is like the simplest thing that we can derive our equations of motion for, or one of the simplest at least. So we apply the Kane method on this robot, and then I exactly clarify for you what is VR. So before we can do that, step number 1 of the method says define the preliminary information. What does that mean? So if this is my 2 degree of freedom planar arm, now in this case there is a little bit difference with the 2 degree of freedom planar arm that I had previously. In this case, I assume that each member here has all of its mass concentrated at the end. So it's not like 2 uniform bars where the center of mass is in the middle or somewhere in the middle. It's not like that. It's like 2 pendulas, basically. One pendulum with no mass, all the mass is concentrated at the end, followed by another pendulum, and again the whole mass is concentrated at the end. So this is a little bit different than our regular 2 degree of freedom planar arm. And you might say, well, what if I want to really use this one? I'll show you. So we go with this example, because this is a little bit actually easier than this one to describe the Kane method. If you want, then we'll talk about how to go about this uniform mass distributions. So here we're going to focus on this example, and then what are the preliminaries? So first describe the geometry. We just did. We said this is like 2 pendulas, right? Massless length, and all the masses are concentrated at those 2 particles, 2 endpoints, which we call them P1 and P2. The torque TA is applied to link A, okay, and it is measured from the inertial frame, or it is applied by an inertially fixed actuator. So the motor that you have here, to apply the torque TA, the bottom of that motor is attached to the ground. On the other hand, the torque that you apply to the second link, TAB, that one is coming from a motor that the bottom of the motor really is attached to this link A, or object A. So if you have this motor here, this motor is rigidly attached, as I said, to block A. It's a relative, basically, connection. It's not inertial connection. or connection to to another rigid body, which itself is moving. We are also going to use 3 sets of unit vectors or 3 sets of frames, just like what we did in the DH convention. Frame A, including A1, A2, and A3. Here, A3 is out of the board toward us. They are rigidly attached to object A, the first link. Frame B1, B2, B3, again B3 out of the board. They are rigidly attached to block B. And then we have the inertial frame N1, N2, and N3, and these guys are really the ground, right? They are attached to the ground. They are inertial frame. So just like the DH method, I use very similar to that or identical to that A1, A2, A3, B1, B2, B3, and N1, N2, N3, and I have explained all of them for you. So here we describe the geometry of the system, the coordinate frame that we use, and these are called the preliminaries. That's step number 1. Step number 2 is what generalized coordinates and what generalized speeds are you going to use. So here we distinguish between speed and velocity, okay? Here when we say generalized coordinate and generalized speed, the generalized coordinate, just like Lagrangian, that we use are Q1 and Q2, the two that best describe the degrees of freedom in the system. And generalized speeds are like the time derivative of these. So we use Q1 dot and Q2 dot. And to avoid showing dot all the time, we basically use a notation U1 and U2. So the time derivative of this generalized coordinate is what we call generalized speeds, and we call them here U1 and U2, which are the same as Q1 and Q2 dots. Now, step number 3 is to develop the required or requisite linear and angular velocities. If we want to include the work or the power, right, as we described it early, by anything in the system, including external forces, external torques, and anything for that matter, what kind of linear and angular velocities do we need to include for the definitions of this VR? In other words, look at your system, see where is it that any external force or torque is applied. And when those forces or torques are applied, they are going to be the cause of what kind of motion? They are going to be the cause of a linear motion or the cause of what? An angular motion. And whatever that is the effect of those external forces or torques, whatever the velocity is the direct result of those, include them here. So if I look at my system, what do I have? I have 2 gravity forces, right? M1G and M2G. By the way, in this system, we assume both of the blocks have the same mass M. So I have mg here and I have mg there, gravity forces. The end effector here is completely free to move, so there is no force here. There are reaction forces from outside of the system at point O. So I can call them OY and OX. And of course, I also have these 2 torque terms. So there are these 6 terms if I want to draw the free body diagram of the entire system. Now, out of the 6, definitely OX and OY do not do anything because they are applied to points that do not move. So OX and OY do not cause any motion, so what? I can eliminate them from my list. They don't cause anything. What is the effect of TA? Well, TA is to rotate link A. So if this link A is rotating and I call the angular velocity of link A omega A, then definitely omega A is one of the required angular velocities. The same thing for T of A with respect to B. The goal of this guy is to rotate link 2. So if I call angular velocity of link 2 omega B, then omega B is one of the required things. And you see here I call link 1 and link 2 A and B. What else? I have mg forces applied to these mass particles P1 and P2. And you know, definitely when you have a force applied to a particle, that particle would get acceleration, linear acceleration A, and then A causes some V. So the goal of this mg is to move particle P1. So velocity of particle P1 is definitely something you want to consider. That's the effect of that mg. The same thing for this mg, it should create Vp2. So clearly you see your required linear and angular velocities of omega A, omega B, Vpa, and Vpb, because that's where those external forces and moments who cause any motion are in effect. And that's exactly what you see in step number 3, that we have to use omega of A, omega of B, V of PA, and V of P1, and V of P2. And we also need to determine how much they are. So since these are velocities, definitely their magnitude depends on what? Depends on u1 and u2, the generalized speeds, as well as the geometry, which in this case is L. Remember, the length of each one of these members is L. So they depend on L and u1 and u2. And their direction should be described in one of these 3 coordinate frames that we have. Either A1, A2, A3, B1, B2, B3, or N1, N2, N3. Okay, so if I can describe them, that's all I need. So how can I do that? Here I can do it based on very simple rigid body kinematics. So omega of block A or link A is definitely u1 times A3. Why? Magnitude of it is u1 because definitely block A is rotating with angular velocity q1 dot, correct? So q1 dot is the same as omega A. And the direction of it is about what axis? It's about A3. Right? Because A is what is attached to this rigid body. So basically what I'm calculating here is omega of A written in A, basically. The omega of that rigid body measured in its own body attached frame. And since this rigid body has A1, A2, and A3 is out of the board, and your rotation is about the axis out of the board, correct? So omega is going to be the magnitude of it times the direction of it. So u1 times A3 is very obvious. The same thing for link 2. Link 2, the magnitude of the rotational velocity of it is u1 plus u2, or q1 dot plus q2 dot. And again, since frame B is attached to second link, the axis normal to the plane for it is going to be B3. So u1 plus u2 times B3 is omega B. And why is it that you add these two together? Because the angle Q2 is relative to member 1, it's not relative to the inertial frame. So I have to add Q1 dots and Q2 dots together, correct? So this is so far for the omegas, which were quite clear. Now let's talk about velocities of each one of these particles. So first we need velocity of this particle P1. P1 does rotate about O, and as you know, when a point is rotating about a fixed point, velocity of it, V equals omega cross R, as you know. And omega here is U1 in the direction of A3, and R for it in this case is this vector. So this is going to be L in the direction of A1. And if you do so, what will you get? Well, you get U1 times L, and then A3 cross A1 is going to be A2. So there's going to be LU1 in the direction of A2. Again, A2 comes from A3 cross A1. So LU1, right, which is LQ1 dot, in the direction of A2, so this direction. This is going to be V of P1. Absolutely it is. You know that from dynamics. And that's what you see here. And then we need V of P2, and for that, now that we have V of P1, I go to rigid body B, and V of P2 can be found through V of P1 and omega of the rigid body. So V of P2 is going to be what? It's going to be V of P1 plus omega of this rigid body cross the R between these 2 points. V of P1 is already LU1A2. Omega of rigid body B, as we found it, is U1 plus U2 times B3. Cross, what is R? The R is this vector, so there's also L in the direction of B1. So if we do that, again, we have B3 cross B1, so that's going to be B2. And so you will get LU1 A2 plus L times U1 plus U2, the whole thing times B2. Right, so this guy is your velocity of particle B, and exactly you can see that's what you see here. So now I have determined the required linear and angular velocities of the system. Using these, in the next step, I can determine those partial velocities, those VRs, or omega Rs, that I need to use in my formula. Okay, so that's step number 4 now, determining the partial linear and angular velocities, the VR or omega R terms. Okay, so let's go ahead and do that. This step is not hard at all. Once step 3 is done, step 4 is no big deal, because these VRs and omega Rs, these guys, are really the coefficients of the generalized speeds in the expressions for angular and linear velocities. So you form a table like this. On the left column, you arrange all of these 4 terms: omega A, omega B, VPA, VP1, VP2. And you give a subscript R to each one, because here you have 2 R's. Remember, you have 2 degrees of freedom. R always goes from 1 to N. N is the degrees of freedom, and here N is 2, so R only can be 1 or 2. So these VRs or omega R's that you have, they either belong to R of 1, the first degree of freedom, or R of 2, the second degree of freedom. Okay, so now what do you do? For omega RA, when R is 1, what does it mean? What's the meaning of this? So when I say omega A number 1, what does it mean? It means the coefficient of generalized speed 1, which is U1, in omega A. So you can also write it as partial derivative of omega A with respect to U1. Right? And omega A number 2, can write it as partial derivative of omega A with respect to u number 2. Or the coefficient of it, really, because they are all linear terms. If they are not linear, you have to use partial derivatives, but they are linear. So what do you get? How many coefficients of u1 do I have in omega A? I have A3, that's the coefficient, so it goes here. Do I have any coefficients for u2 in omega A? No, it's like u2 times 0. So the coefficient of u2 is going to be what? 0. Similarly for omega B, what's the coefficient of u1? That's B3, so it goes here. What's the coefficient of u2? Again, that's also B3, so it goes there. When we go to V of P1, what's the coefficient of u1? That's LA2. Do I have any u2 terms? No, so we can write it as 0 times u2, and so that 0 goes here. And finally, what's the coefficient of u1 in VP2? Well, I have one place LA2, the other place I have LB2. They are both multiplied by u1, so it's going to be LA2 plus LB2, or you factor out L. What do you have for u2? You have LB2 multiplied by u2, so you get it here. Right? So just that simple partial derivative or the coefficient will definitely get you what you wanted. So now that my table is good, I got all of these VR terms and omega R terms. I'm ready to use them into my Kane method formula. So I've got these parts covered, except for F's now. The F and the F star, you have to take care of them too. So that's why in the next step, we have to calculate the accelerations. And you might say, well, you just said forces. What happened to accelerations? We need the accelerations. Why? Because these inertial forces, Fr star, if you remember, they are the masses times the accelerations. Correct? Just go back here. For a single object, this F star is negative m times a. So I need to know a in order to determine F star. So I need to know here the acceleration of the system, linear or angular, that I need in order to go to step number 6. So if I don't know step number 5, I cannot go to step number 6. So let's go ahead and determine the accelerations that I need for step number 5. Again, for acceleration of the two particles P1 and P2, I use the rigid body kinematics. Now pay attention in this case, because all the mass of the system is concentrated into the two particles P1 and P2. All I need to find is the linear accelerations, AP1 and AP2. I do not need an alpha, because alpha is important when you have inertia matrix I to multiply by that, and it gives you a torque, right? But in this system, these blocks do not have inertia because the rigid bodies have no masses. All the mass is concentrated at the particle. Okay, so the rigid bodies themselves are massless, so they don't have I, so I do not need alpha. Just keep that in mind. Okay, so now how do I find them? Again, as I said, basic rigid body kinematics. So what is A of P1? P1 is rotating about the fixed point. So A of P1 is going to be what? Is going to be A of point O, right, which we know is 0, plus alpha of member A cross R of P1 with respect to O, and then plus omega of member A cross omega of member A cross R of P1 with respect to O. As I said, we know this guy is 0. Alpha of A, remember omega of A was what? Was U1 in the direction of A3, correct? That's what we had right down here. So what is alpha of this member? Alpha of A is definitely what? U1 dot in the direction of A3, correct? This is all planar motion. You might say, well, when you take time derivative, A3 does have derivative, doesn't it? No, not in this case. Because A3 is always perpendicular to the board out of the board, so A3 does not change its direction, so it doesn't have time derivative. So in this product, the only term that has a time derivative is the first one. That's alpha of A. So let's write it down. That's U1 dot A3. This R vector, as we saw it last time, it is L times A1. And omega, we just said it, omega is U1A3. And if you simplify this, here you have A3 cross A1, which is going to be A2. So it is going to be LU1 dot A2. And the next term is going to be negative magnitude omega squared times R. So it's going to be negative L, magnitude of it is U1 dot, square it in the direction of A1. So this is acceleration of particle P. It has two terms. We have this tangential acceleration and we have the centripetal acceleration, right? So we have one term here toward the center and we have one term here, correct? And we know all of this from dynamics, correct? And that's what you can see here. And then for A of P2, we repeat the exact same thing, right? A of P2 is equal to A of P1 plus alpha of member B cross R of P2 with respect to P1, and then plus omega of member B cross omega of member B cross R of P2 with respect to P1. And again, A of P1, you directly have it, so you can just go ahead and bring this guy down, right? That's directly given to me. Alpha of member B, remember omega of member B was what? Was U1 plus U2 in the B3 direction. So alpha of member B, again, since B3 is always perpendicular to the board outward, has magnitude 1, has no time derivative, so it's going to be simply U1 dot plus U2 dot in the direction of B3. So I can write it down here. This unit vector is L times B1, as we saw last time. And this omega, as we saw, it was what? It was U1 plus U2 times B3. And if we carry this out, you will get whatever A had, which was L U1 dot A2 minus L U1 squared A1, and then plus the relative term. Because here you have B3 cross B1, so it's going to be B2. It's going to be plus L times U1 dot plus U2 dot B2. Then minus L times, as you can see here, U1 plus u2, the whole thing squared in the direction of b1, and that's acceleration of p2, and again you can clearly see that here. So now I found the linear accelerations I want in the system to determine those F star R terms, right? The R generalized inertial forces FR star or F star R, right? How do I find them now? Well, in order to find those, we multiply each one of these accelerations of these particles by the corresponding mass and then dot product it with VR of that particle, right? Because remember here, we define FR star as VR dot F star. But now you have more than one V. You have several VRs. Since you have several VRs, each one of those terms that you dot product, now you have to add them together to get what? To get the total F star R. And that's what you see here. This negative MI API, that whole thing, is your F star of I. The inertial force of particle I. You dot product that with the velocity of that particle and sum them all over all particles, and that give you F star R. And there are two of these F star R's, one for R of 1, one for R of 2, and if you expand it, you should get these two terms for F star 1 and F star 2. Let me show you one of them at least, right? So you know how these terms are calculated. So let's say F star 2. How do I calculate F star 2? F star 2 means R should be equal to 2. So what do you get? F star 2 equals what? Based on this formula, is negative of R is always 2, but I can go from 1 to 2 because n is also 2, right? N is the same n that you have here. So I goes from 1 to 2, and R one time goes 1, one time goes 2. So let's plug in I of 1 here. You will get V1. Remember, R is R is 2. So V2, because R is 2. Right? Of P1, first I goes 1, dot M1 A of P1, then plus V2 P2, or V of P2, the two components of it, the second component of it, dot M2 A of P2. So this is how we expand it. Now, what do we get? Well, let's go ahead and find these partial velocity terms, V of P1, 2, and V of P2, 2, correct? We can find them from my table, correct? So V2, so I have to go under R of 2, and one of them is V of P1, one of them is V of P2. So V of P1 for 2 is this guy. V of P2 for R of 2 is this one. So the first one is what? 0. The second one is LB2. M1 and M2, in this case, they are both equal to M, so I can get rid of this subscript. What is AP1? What is AT2? I have them both here, right? So first of all, I don't need to write AP1 because it will be multiplied by a 0. So this term I can completely neglect. All I need is this AP2, which I already have down there, right? So I will bring that whole thing and plug it here. And what will you get when you expand? So all I need really is to dot product this term with that term over there. and there is negative and there is m. So I bring m out with the negative, it becomes negative m. And then what? Now it's going to be LB2 dot what? Negative LU1 squared A1. So if you want, I can write it for you. LB2 dot negative LU1 squared A1. This is the first term. And then what? Again, LB2 dot, now you have the second term, LU1 dot A2. Again, LB2 times, or dot product. The next term is negative LU1 plus U2, the whole thing squared B1. And finally, plus LB2 dot, and you have what? LU1 dot U2 dot. B2. Okay, so this is the expansion. Now, if you look, all of the terms have L squared in them. There is L and L, there is L, 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 and L. So if you want, I can bring that L squared out here and get rid of all of those L's. So now what I need to focus on is B2 dot A1, and there is a negative here. So what's the result? It's negative of B2 and A1. So what is B2 and A1 dot product? This is B2, this is A1. Clearly you see the angle between them is 90 degrees plus Q2. Because this angle, if you draw A1 here, this angle here is Q2. So the angle between B2 and Q1 is 90 plus Q2. So when you do dot product of two unit vectors is magnitude first one, magnitude second one, which is 1 and 1. So it's going to be cosine of 90 degrees plus Q2. Here you have B2 and A2. Clearly B2 and A2, the angle between them is the same as A1 and B1, and that is Q2. So definitely here you will get one more thing here. This U1 will come out as well, and it doesn't have a hat because it's just a speed. So this one is going to be what? It's going to be U1 dot, and then B2A2, as I said, is cosine of Q2. Correct? What about here? B2 dot B1. We know B1 and B2, they are perpendicular to each other, so the whole dot product is going to be 0. And here you have B2 dot B2, which is 1. So all you will get is really U1 dot plus U2 dot times cosine of 0, which is 1. So if I want to simplify, you will get what? Negative ML squared times what? From geometry, you know cosine of 90 plus an angle is negative sign. With that negative sign, it becomes positive sign. So it becomes U1 sine Q2 plus U1 dot cosine Q2, and then plus U1 dot plus U2 dot. Or you can factor these two out to say U1 dot times 1 plus cosine of Q2. So it's U1 dot times 1 plus cosine Q2 plus U2 dot plus U1 sine of Q2, the whole thing times negative ML squared. That's exactly what you see here. C2 here means cosine of Q2. And if you do this time expanded for R equal 1, you will see that F1 star is going to be that whole big thing. Okay, so now we have to calculate the generalized active forces and the equations of motion. So for generalized active forces, what we need to do is to dot multiply any active force or torque by the velocities of the points or the bodies to which they are applied and add them together. So if you remember, we look at the free body diagram or the robot here. We had TA and TAB, right? As well, we had these MGs. We learned that there are two forces. If I look at the free body diagram of the entire robot, there are two forces at O as well, OX and OY, but they are not active forces. They are applied to a stationary point. That point does not have a velocity. So those two we can exclude from our calculations and formulations. These two mg's, if I want to write them in terms of the unit vectors, they are definitely negative mg times n2 direction, correct? And so now, since these two forces are applied to P1 and P2 and they are particles, so for each one we need the velocity of the corresponding particle. So I need velocity of P1 and dot product the other one by velocity of P2, and then the torque TA that is applied to rigid body A, that should be dot producted by omega A because that causes a rotary motion. And similarly, T of AB that is applied to block B, that should be dot producted by omega B because that's the cause of the motion. So when we do the dot product of these four terms and add them together, that is the total active forces that you have. And remember that the definition of power that I initially described for you, power, if the system is a linear system, it is going to be V dot F, I'm sorry. If the system is a rotary system, it is going to be omega dot T. Okay, so that's what you see down here. That so if we go down here, you can see these four terms, right? This one, this one, this one, and this one. So they are all clear. The only thing I might need to explain is here, why is it that omega A dot producted with TA minus TAB, not just with TA? The reason is when you have this rigid body A, it has this motor on it, and this motor is turning rigid body B. So the torque that you're applying to block B, object B, you call it TAB. The reaction of that is applied back to the motor, and motor is rigidly attached to block A, so you have a reaction TAB backwards on block A, and you also have this T of A. So this TA was in the direction of A3, if you remember, and that TAB is in the direction of B3. Okay? And because this is a reaction, use that negative sign. So here I have to add those two together, which is the net torque on block A, and that causes the rotation omega A. So that's why we have subtracted. One term is the reaction. Okay, so now this is the FR. Now R can be 1 or 2. So if I apply R of 1, one time I get F1. If I apply R of 2, I get F of 2, and then I get both of my basically generalized active forces. So let me show you one of them. For example, here, if I apply R equal 2 here, what's going to happen? So when R is 2, I need omega B of 2, omega A of 2, VP and VP1 and VP2 of 2. So basically, I need to go to that table and I need to look at the second column. So these are the terms I need: 0 B3, 0 LB2. And if I go down here and basically consider them, this one was 0, and this one is LB2, this one is B3, and this one is 0. So if you expand, it is going to be LB2.mgn2 and then B3.tabb3. So this last one is very easy because B3.B3 is 1, so you're just going to get TAB. That one is going to be negative mg times L times B2.N2. And for that, I can go up here. That is B2, N2 is upward, and the angle between B2 and N2, this angle is clearly Q1 plus Q2. So it's going to be cosine of Q1 plus Q2 here. So this should be equal to F of 2. And if I go down here, you can see that's exactly the case. Instead of cosine of Q1 plus Q2, I've used the short form notation C1, 2. And definitely if you apply R of 1 here, that you need to go and choose the first column variables. Then if you plug in, you will get this F1. And now since you have F1, F2, and F1 star and F2 star for each R, you add them together. So first you get F1 plus F1 star equals 0. That gives you this equation. Then you say F2 plus F2 star equals 0. That gets you the second equation, correct? So these are your two equations of motion derived by the Kane method. And that's it. Now, as I said, they might not look so easy here, but as I said, when the degrees of freedom go further and further up, this method is quite systematic and it is much easier to go even compared to the Lagrangian method. So it really shows its advantages when the degrees of freedom go up, or as I said, when you have some constraints or external forces or some addition to the system and you do not want to start from scratch and rederive everything. I'll show you in a minute that's the case. With this method, adding some stuff to the system, extra forces, extra constraints, and so on, we can still use whatever equation that we have and modify them a little bit and get the equations of motion for the new system. While with other methods, it's not that easy. For many of them, you have to redo a bunch of things or all from scratch. Okay, so when it comes to complicated system, this method can be the method of choice. The last thing before I go to those extra advantages is, if you remember, I told you that we call these FRs or FR stars generalized active forces, and I said that these VRs or these omega Rs, they don't have the unit of, let's say, meters per second, they have the unit of 1. Okay, that's why we call them generalized forces. We don't call them powers or activities anymore. Why is that? You can see here from the table. If you look at the units here, for omegas, the unit is 1. For V's, the unit is meters, right? Because look, here it's just a unit vector, right, for omegas. And for V's, it is the unit of length. So you don't see the unit of time anywhere, anything divided by unit of time. So if I want to say more accurate, it's either meter or like 1. Okay, so you're not really multiplying the force by meters per second to get a power or something. It's just like you are literally multiplying a force by a meter, or you're multiplying a torque by a 1. So the unit is going to be like Newton meter, which is kind of like a work, really, or joules. So we can say that really the unit of these generalized forces is not even force, and it's not power. It's kind of like joules. The unit of them is the unit of work, really. That's why we call them active force, or the force in action, right? The effect of force in action. So just keep that in mind. Good? So now let's go ahead and talk about modifications. If you want to add something to the system, what should you do to the equations you have already derived? So now let's consider that we have added a force at the end effector. What should we change? Do we change any of our VR or omega R terms? Absolutely not. Especially because here the particle P2 is already at the end effector, and I do not need to add any extra motion or velocity where that new force that I mentioned applying at the end effector is happening. That area, the velocity of it is already considered in my VR and omega R terms, so I'm good. What about the inertial forces? No change. The only thing you need to change is the active forces, because now you have some extra term that you should add to your active forces. Now you have this new force, right? Fxn1 and Fyn2, and that is applied to a place for which the motion is called Vp2. So now you have to add what to it? You have to add basically this new force and dot producted by Vrp2. Dot producted by this new force Fxn1 plus Fyn2. That's all you need to add, and is clearly mentioned here for you. So you plug R of 1, it gives you one term to be adding to the active force F1. So you're going to have some extra term added here. And if you put R of 2, it gives you one term to add to what? To R of 2, and that's all it is. Everything else is the same. You will get the same equation of motion plus some extra terms. You might say, what about if I have some viscous damping at the joints? Can I add that? Sure. What do I need to do? Again, those are active forces or torques, so we have to just modify where those are happening. And guess what? One of them is like TA, it is affecting the first joint. One of them is like TAB, it is affecting the second joint, correct? So if I want to show them here for you, the first viscous friction is happening here, the second one is happening here. So the first one should be dot multiplied by omega R of A, whatever it is. And this one should be dot multiplied by omega R of B, because that's similar to the torque TAB is going to rotate member B. That's all it is. And here we go and take a look at these terms. You clearly see what I said. Now, what are they? Let's say what is the second viscous friction at the joint? Well, if you remember, viscous friction is what? The viscous friction at the joint is formulated by T equals some coefficient B times the angular velocity at that joint, Q dot. So this is the formula for a viscous friction at a joint, a rotary joint. Now, the second joint that I have, we know this is its angular velocity. U1 plus U2, or Q1 dot plus Q2 dot times B3, correct? That's the Q dot for member 2. And here you call the coefficient of viscous friction for it, you call it BT2. And it is a negative term. Why negative? Because it is opposing the direction of motion, right? Or the way that the motion is happening. So if this is going this way, that damping viscous friction is like this. This is, you might call it T of B or T of B1. And this guy, you might call it T of B2. So because they're opposing the motion, you definitely want a negative sign. And that's, again, what you can see here. What about the first joint? Well, the first joint, the angular velocity of it is U1A3. U1 is Q1 dot. The coefficient at that point, you call it BT1 with a negative sign. And you might say, what is this guy? And this guy is the same as this one on the right. But instead of negative, it's positive. What is it? It's again action and reaction. If you remember here that we included negative TAB for the first member. Why? Because we said the motor is attached to member 1. So if you apply a TAB by motor to member B, reaction of that is applied back to what? To member A. The same thing happens about this viscous friction. If this TB2 is applied on the shaft of motor or link of member B, then the reaction of that, which is this way, is going to be applied back to the motor, and motor is attached to member A, so it is going to be applied to member A. So it is going to be this minus that, okay, the total negative or the total momentum due to viscous friction. And that's what you can see here. So it is quite clear that if I want to add a viscous damping, or if I want to add, let's say, a force at the end effector or so on, all I need to do is to add one or several terms to what? To my active forces. Because my inertial forces are the same, and in this case, as long as I'm not adding a degree of freedom or anything, or applying force or torques to a new location, I do not need to add anything to my partial velocities. That's all it is. Now, sometimes you do have to add something to your degrees of freedom or to your partial velocities. Sometimes your degrees of freedom are changed because you are applying a constraint. Okay, and again, this method is well capable of handling that. Let's say, for example, here you have the same 2 degree of freedom planar arm that we talked about, but now you limit the end effector or point P2 to move inside a horizontal groove, and this horizontal groove has no friction. Here, just to make it a little bit easier. How do you change your equations of motion or adjust your equations of motion to accommodate for this extra constraint that you have, right? So what you can do here is to add an extra particle, P3, right where P2 is, okay? because P3 is also the end effector. So there is an overlap, right? They are coincident, P2 and P3. And P3, adding P3 will add one extra degree of freedom to the system. So P3 with respect to P2 can move horizontally this way. Okay, so now you have this degree of freedom, you have this degree of freedom, and you have that degree of freedom, Q1, Q2, and that's whatever you want to call it, D3 maybe. But now you have two constraints added to your system. What are they? Well, here, the velocity of this point P3 can only be in the horizontal direction, as we said. It cannot have a vertical velocity. What is velocity of P3? Velocity of P3 is the same as velocity of P2. And what is velocity of P2? So we had the velocity of P2 earlier, right? I assume we calculated that somewhere here. But now we have to dot product this along x and y directions, or n1 and n2, to get the horizontal and vertical components, because the constraints I have applied are with respect to the inertial frame, okay, about n1 and n2. So what I really need is v of p2 dot n2, vertical direction, the vertical component of velocity of p2, which is going to be exactly this guy, L1 C1 U1 plus L1 C1 2 U1 plus U2. That has to be 0. And that is not very hard to see, because your V of P2, if you remember, it was L U1 A2 and then plus L times U1 plus U2 B2. So you dot product it with N2. And so here you have A2 dot product with N2 and B2 dot product with N2. And remember, A2 is this direction and N2 is this direction. So the angle between them is this Q1. So correct. So you should be getting L U1 and then A2 dot N2, as I said, is cosine of theta 1 or cosine of Q1, which we show by C1. So that's this term. And the next term is L U1 plus U2 times B2 dot N2. B2 here is this vector, which is perpendicular to member number 2. And this angle is Q2. So the angle between B2 and N2 is Q1 plus Q2. So that dot product is going to become cosine of Q1 plus Q2, or C12, which you can see here. So this is your second term. So adding these together should be 0. And that gives you the bottom equation, the first constraint that you have. The other constraint is, now if you call the generalized speed associated with this horizontal motion U3. Remember, you had U1, which was Q1 dot. You had U2, which was Q2 dot. And now, if you call this maybe Q3, this horizontal motion, then U3 is going to be Q3 dot. So it says the horizontal component of Vp2 should be equal to U3. And this is exactly that. This is V of P2 dot N1. This thing should be equal to U3. So you see, I added one extra degree of freedom to the system, Q3 now, which is the horizontal motion between 2 and 3. But it came with two extra constraints. So my degree of freedom of the system, that was 2 originally, I added 1 to it, and then I subtracted 2 constraints, so now I really only have 1 degree of freedom left. I have 3 generalized coordinates, but one of them is really independent. The 2 other depend on this degree of freedom. And the question is, how can I relate, let's say, 2 of these degrees of freedom, let's say Q2 and Q3 to Q1, or their velocities together? For example, can I relate U3 and U2 somehow to U1? If I can do that, then incorporating these constraints into my equations of motion is not going to be necessarily a hard thing. So here we answer the question in general that if you have n degrees of freedom and you add m constraints to the system, then you really need n minus m degrees of freedom in general. Not always it is easy to just find some based on some others and replace from the constraints. Sometimes the constraints are non-holonomic, sometimes they are holonomic but highly nonlinear. So the better way and the easier way to incorporate it is if you can basically work on the generalized speeds instead of generalized coordinates, right? If you work on generalized speeds, u1 all the way to un minus m. The n minus m, let's say, use that, you might think they are the independent, basically generalized speeds. If you can find any other generalized speed in the system outside 1 to n minus m, which is basically from n minus m plus 1 all the way to n. If you can find all of those based on these other generalized speeds in a linear fashion, so uk here, where k can be any number from n minus m plus 1 all the way to n, you can find any uk based on the linear combination of those other u's, which are from 1 to n minus m, as what? As alpha, some alpha times those u's plus some beta in general. So a linear combination of those u's plus at most a constant. If you can establish such a linear relation between those redundant generalized speeds and these independent ones that you want to consider for the equations of motion, if you can do such a thing and determine these alphas and betas, then all you need to do to the previous equations of motion that were fr plus fr star was equal to 0 is now you have to add a summation to it. And the summation is this. K goes from n minus m plus 1 to n, as I said, this area, over those extra or redundant degrees of freedom, of what? Alpha kr, the same alphas that you found, times fk plus f star k, and then set it equal to 0. The constants beta of those relations do not play any role in the modified equations. And this is very advantageous because you have already this one set up. All you need is to find the summation terms, find these alphas, of course. First, you have to form this set of equation, find the alphas, and then add the summation to your previous set of equations and get what? Get your new set of equations. For example, let me explain that with the example. If we go and look at this 2 degree of freedom planar robot that we have, we just found that we can add this extra degree of freedom, or this generalized speed, this extra generalized speed u3 to the system, q3 or u3 here, and that comes with 2 extra constraints, right? Now from these constraints we can easily find 2 redundant generalized speed based on another one. So here your n, as I said, is what? N was 2, but now you have 1 extra degree of freedom, so your N becomes 3, but you have 2 constraints here, correct? Therefore, you really need one of these generalized speed to keep, and you can basically determine the 2 others based on that. So in here, if I want to keep U1, then I want to determine U2 and U3 based on U1. How do I do that? Well, from the bottom one, it's very easy to see that LC1U1 plus LC12U1 is LC12U2. So U2 can be written as, basically, if you eliminate the L's, this is going to be negative C1 negative C12 divided by C12, the whole thing times U1, right? And that's what you can see down here. And from the bottom one, also top one, if you want, you can also find U3. So from here, your U3 is going to be a relation between U1 and U2, and from here you can really replace your U2 relation that you had up here, and if you do that, then your U3 is going to be really S1 plus S12 times U1, correct? And then minus S12U2, but U2 is this guy here, so you can replace it, then multiply the whole thing by L, right? And if you simplify that, that should give you a relation between what? Between U2 and U3 and U1, and this is the simplified version of that if you do a little bit of algebra. So U2 and U3 can now both be found as a linear relation of what? Of the other U's that are independent. As I said, in this case, since n minus m, the number of required really degrees of freedom is 1, all you need to keep is U1. So you have to find all other U's based on U1, and we did that. And the relation that we found, they are linear relations. When I say linear, it doesn't mean these coefficients that we call alpha here, alpha 2,1 or alpha 3,1, they are necessarily constant numbers. No. They can be these alphas what? Functions of the angles. And you see they are functions of cosine or sine of the angles. So this alpha 2,1 is really a function of vector q. The same thing with alpha 3. Okay, they are not constant. Even if you had a constant term beta, you had some beta, let's say here, right? Beta 2,1, that could have also been a function of q. So when we say constant, it doesn't mean really a constant number. It means it does not, the alpha or beta does not depend on u. So the relation is linear in terms of u's, not in terms of the q's. Okay, now in this case, there is no beta, so all you have is just alpha 2,1, which is this term in the box, and alpha 3,1, which is the other term in the box. Good? So keep that in mind. Now, if that is the case, I want to add this summation term for myself to my previous equations and see how that will change my equations. And the thing is this. This time your r goes from 1 to n minus m. It doesn't go 1 to n. It goes 1 to n minus m. And n is 3, m is 2. So it becomes 1. So the only real r value that you can choose here is 1. There will be no 2. There will be no f2 or f star 2. There is only 1. So what's going to happen to this equation? It becomes f1 plus f1 star, the two terms that we already have calculated, plus summation of k goes from n minus m plus 1 to n. N is 3 here. K n minus m plus 1 is 2. So K goes from 2 to 3 of this. So it is going to become what? Alpha of K. K when is 2. It's going to be alpha 2, 1 times what? F of 2 plus F star of 2. And then K becomes 3. It becomes alpha 3, 1. F3 minus F3 star, or plus F3 star. This whole thing becomes equal to 0. Now, in the previous scenario, I have already calculated for you F1 and F star 1, F2 and F star 2. So I don't need to recalculate them. Alpha 1 and alpha 2, I just calculated for you based on the constraint. The only thing we need to explain is what? F3 and F3 star. If I know them, then it's over. My equation of motion is done. And the question is, what is F3 and what is F3 star in this case, right? So F3 in this case is 0. Why? Because F3 means what? Means the active forces, the generalized active forces on P3. Well, P3, or this particle that we put on the end effector, there is no active force on it because the only 3 forces that are acting on it are what? From outside environment. Is mg, or mg is already actually calculated. I don't even need mg for that. Because this is really, this is like a massless particle, this P3. The mass of it is already considered in P2. So the mass that you associate with P3 is actually really 0. Unless this end effector here is to grab something in this slot and want to basically manipulate and move it. If that's the case, then yes, P3 can be considered a separate particle with mass m3, and you can consider that, as you can see here down in this equation, there is some m3 is considered, and because in that case we are explaining or describing the problem in a different manner. We don't say we force the end effector to move in the slot. We say the end effector has gone into the slot to grab a particle of mass m3 called P3, and now it is moving it. Okay? But again, if the end effector is just to move inside it without really grabbing some particle P3 with mass m3, then you can use 0 for m3. So, but even at most, you have this m3g, which is definitely not an active force. Why? Because the end effector here with that particle or itself has to move horizontally. This force is acting vertically. The normal force from the walls also is not an active force. It doesn't do any work, right? So there is no force. The only force that could have existed and had any contributing general active force was friction, which would be in the same direction as U3 or opposite to that. But here I said there is no friction in the groove, so that's it, and therefore there is no active force. Therefore you can say my F3 is simply what? Equal to 0. If there was a friction, then you have to add the velocity of particle 3, right, for the r that you have, and here you actually only have one r, and dot product this with that friction force, which was equal to negative of mu k times n, which in this case is mg, and then in the n1 direction. Okay, so then you could do it like that, but in this case, since there is no friction, F3 is equal to 0, and then your inertial generalized force, as we all know, is equal to negative m times a, and a is u3 double dot, because u3 is velocity, so acceleration of that block is u3 dots, which is like q3 double dot. So negative m3 u dot is definitely what? Your inertial force. So calculating F3 and F3 star is also no big deal in this equation. And once I have those, then I can combine everything together. But you clearly can see that I used something that I have already derived. All I had to add because of this constraint were F3 and F3 star to calculate and these alphas. Once I can calculate these, I combine them with previous information, and now I get my single equation of motion that I will have for the single degree of freedom for R of 1, right? Or U1 basically here. Although U1 alone will not be included, because if you look at your F1 and F2, definitely you will see that if you go up and look at them, your F1 and F2, they included C1 and C2 both in them. And the stars also have U1 dot and U2 dot in them. Okay, so definitely it's not going to be only on U1, U2 will also be included. But you only get one single equation of motion because you really have 1 degree of freedom independent. So hopefully this video was useful to you. This is probably a new topic to many of you, this Kane's method, and you definitely need to practice a lot more and solve a bunch of more problems before you have a good grasp of this method. But as I said, this is really a systematic method for systems with higher degrees of freedom, where the derivation by Newton becomes very, very difficult, and Lagrangian becomes a little bit more complicated, especially Lagrangian when you have constraints and you have to introduce these new Lagrangian multipliers. As you saw here, I did not introduce any new unknown here, really. Not that I didn't, I had to introduce U3, and that's because of the extra motion, but I kind of eliminated really U3 here as a function of U1. So it's kind of implicit incorporation as compared to the lambdas, the Lagrangian multipliers, and then you have to basically include them in all of your extra equations. So thank you so much for your attention, and I will see you in my next video.